Okay, this is Physics 1C for, I think it's recording, yeah. This is Physics 1C for February 18th, and today we're going to go into an introduction of static electricity, what it is and kind of what causes it. And then we'll talk about all the other topics that are listed here. We'll talk about electric charges, conservation of charge, the difference between conductors and insulators, Coulombs Law, which is the force law that tells you kind of how strong the force of electricity is, the idea of superposition of forces, and then we'll introduce the electric field, and then we'll spend the rest of class calculating electric fields. And whatever we don't finish today, we'll finish on Tuesday. All of this content comes from chapter 21. It is a very dense chapter, and yeah. So if you get lost with anything we're doing today, just please don't hesitate to ask, because there are some complicated ideas here. It's going to start off relatively simple, and then it's going to get much more complex by the end of class with a lot of calculus to do some of these latter calculations. Okay, so what is static electricity? So static electricity was first discovered, at least in the Western world, I'm sure it was discovered in other places too, by the Greeks. And the ancient Greeks basically noticed that if you took a piece of amber, so they noticed that pieces of amber, and if you don't know what amber is like a resin that comes from trees, and then it kind of hardens, and it's something that, like, if you saw the movie Jurassic Park, that like mosquito that was trapped in amber that they used to, whatever, that was the kind of science of that movie. But it's this, basically, you can think of it as a piece of plastic if you want to. It's basically just a piece of tree resin that's then come hardened. They noticed that amber, when rubbed with cloth or fur, basically, with some kind of we'll just say with fur. It's the easiest thing to think about, I think. Could basically attract really tiny pieces of like dust and pieces of cloth and stuff like that. So they noticed that we'll just say that it can attract tiny things, not like pieces of metal, but pieces of cloth and stuff like that. And so the word for amber. Okay, amber in Greek, the word for that is spelled like this. You all know that word, I'm sure, electron, except we spell it with a C, but it's still the same basic word. So their word for amber became our word for electron. And that was kind of the first knowledge of what static electricity was the Greeks kind of noticed that this phenomenon happened. This is a long time ago. They also knew about magnetism too. So, so you rub a piece of amber and it could attract little tiny things, okay? Now, nowadays, what we would say is that we could simplify this idea in the following sense. We could say that if you were to take a plastic rod, and this is something you can do yourself if you have like a PVC pipe sitting at your house or something like that. I think it helps a lot if it's hollow. Sorry, there's some issue with this. All right, so suppose you have like a PVC pipe, right? And I'm just going to say that it's some type of piece of plastic, right? Plastic in general, if you take really any object, it starts off as a neutral object, meaning it doesn't have any electricity associated with it, okay? But if you do the same thing that the Greeks did, and you take a piece of like rabbit fur or something like that, so you have a piece of fur, it doesn't necessarily have to be fur either, it could be a piece of cloth, like my shirt would certainly work. So I'm sure your shirts would too. You take a piece of plastic and you rub the fur on the plastic. What ends up happening is something really interesting. So we rub this on here, okay? And the effect is that basically the fur and the plastic, they both start off as neutral. So this is neutral. It has no charge. This is neutral. Okay, but if you rub the fur on the plastic, then the effect is that the plastic itself will actually transfer some little pieces of charge from the fur. The fur is actually going to rub a bunch of charges on it. And the convention that we created to describe what happens here is we say that this rod ends up becoming negatively charged. Okay, so I'll put little negative signs there, but this rod becomes negatively charged. In the modern knowledge of what we know nowadays, we know that what's happened is basically that electrons, in the process of rubbing the fur onto the plastic, basically transfer from the fur to the plastic. So this process basically transfers electrons onto here. Now, if they both started as neutral and they're in contact with each other, can anyone guess what happens to the fur? If the rod becomes negatively charged, what happens to the fur?
It becomes positively charged?
Yeah, so this thing becomes positively charged. All right, so now what can you do with this? So there's a lot of things you could do to prove that there's a negative charge here. One thing is you can replicate what the Greeks did, okay? And I've got a little picture of it. This is something you can do yourself if you want to with like a comb. This one here, we'll take this picture. So if you then take that rod, and I would certainly, okay, I don't know why I did that. We'll just drag it over here. If you were then to take that rod and cut up a bunch of little tiny pieces of paper, and then bring the rod really close to the paper, you'd find that the rod actually attracts those little tiny pieces of paper, okay? Now the paper themselves are neutral, but something happens as described right here. So that's one thing you could notice. The other thing you might notice is that if you were to suspend this rod via some type of a, well, something like this, let's say. So here's a little picture that describes kind of the process. So let's look just at getting a phone call. Close it. There we go. All right. Oops. All right. So yeah, something like there's a lot of stuff going on in this picture here, but let's focus just on this left piece right here. Okay. So you have two plain plastic rods. They neither attract or repel each other, right? You rub the rods on fur. So you've got these plastic rods. You rub them on fur, and then you suspend one of the rods via this little crush right here, right? And what happens is the two rods are going to repel each other. And this is one of the fundamental ideas of electricity, is that if you have two like charges, they repel each other, right? If I have two negative charges, one negative charge here and one negative charge here, and they're just sitting in free space, then there's going to tend to be a force that causes these to repel each other. If you have a negative charge that's near a positive charge, the opposite happens. There's a force that draws these together, right? That's something you probably learned about in one of the first science classes you took. And the other possibility, of course, is you have a positive charge and a positive charge, and those also repel each other, right? In the case of the plastic, if they're both rubbed with fur, they both become negative. So now these are both negative, they repel each other, right? Now, if you want to try this experiment right here at home, I would highly recommend doing it. It's really easy to do. So here's how you can do it at home. You take a plastic comb. So you can basically replace the plastic rod with a plastic comb, right? And for these little pieces of paper here, you basically just take a piece of paper, cut it up in a bunch of little tiny pieces, put them on a table, take the comb. There's two different things you can do. You can either rub it on your hair. I mean, animal fur can be your hair too, right? You could rub the comb on your hair. It would become negatively charged. And then you could use it to pick up little pieces of paper. So you can try that yourself if you want to at home. And you could try some of the other things we'll talk about here in a little bit. Okay. Now the other type of electricity that you can produce is positive electricity. So this is negatively charged. But we can also make positive charges, and the way we do that, the way that at least we talk about in physics textbooks, I'm assuming this must have been one of the first ways people figured it out, how to make a positive charge, because, well, we'll talk about it in a second. So for positive charge, what you do is instead of using a plastic rod, you use a glass rod, and you rub it with silk, okay? The effect here is that the glass will become positively charged, but the silk will become negatively charged. And then if I take a glass rod, bring another glass rod near it, it repels it, okay? Now, how do we know one is negative and one is positive? We don't really know. We came up with a name for these things. And the first person to really distinguish between two different types of electricity, does anyone know who that was? So I can, if you guys are typing anything. Forgot about that.
Franklin? Was that Ben Franklin?
That was Franklin, exactly. So Benjamin Franklin, who is kind of one of our, quote, founding fathers in America, he was known for more than just politics, though, as you probably a lot of you know, as there's this kind of story that he went and flew a kite in a thunderstorm to show that you could, with a key attached to it or something like that, to show that lightning and what we're describing here were the same idea, that lightning was a form of electricity. Okay. He probably never actually did that experiment. I think it was kind of a thought experiment that he was describing. But either way, he was the person that came up with the idea that some of the electricity is positive and some is negative. It's not just... So I guess before that, they thought of it as a... I think they called it like an electric fire. Because it was kind of similar to fire to them in a sense. Anyway, he figured out that there were two types. And this one we call negative, and this one we call positive. And we could have reversed that. I don't want to be too confusing, but this could have just as easily been called positive, and this one could have been called negative. It doesn't really matter. You have two types. You could call it type 1 and type 2. But the difference is, or one thing about them is that when you combine the positive and negative together, if you have equal amounts, you can neutralize them and you can get a neutrally charged object, like what these were here. Anyway. And of course, once something's become charged like this, it's not permanently charged. given enough time, one of these plastic rods will eventually lose this electricity. It'll lose this negative charge that it's gained, right? And there's different ways you can do that. One of the simplest ways is to just take it with your hands and rub all over this, and eventually all that excess negative charge will kind of transfer into your hands and into your body, and then down into the earth. The earth is basically a reservoir of negative charges and positive charges. It can absorb as many negative charges as you want. It can give as many negative charges as you need. So, yeah. All right. So what are some other things that we can say about this? Well, as I mentioned, when we do this process of rubbing, okay, whether we're rubbing fur on plastic or silk on glass, then that process has the effect of transferring charges, okay? So they start off neutral, but the fur becomes positive. So one way you can prove that is you could basically, after rubbing the fur on the plastic, you could bring a piece of fur which is positively charged close to your plastic rod, and you'll show that it'll be attracted. And I wish we were at the school. We can do all of these demos at the school. I can't really do them in my home, though. Anyway, but like I said, you could try this yourself. Take a plastic comb, rub it on fur, or like on your shirt or something like that. Really, the more hairs, the better. So if you've got like nice long hair, I don't have long hair, but if you have nice long hair, it's pretty good for doing this. So you rub the comb, and then you take a bunch of little pieces of paper and bring the comb really close to them, and you'll see magically that the pieces of paper lift up to the comb. Okay. Okay. Anyone have any questions so far? Went through that kind of fast, I guess. All right. So why does this work then? Okay. These little pieces of paper are, I guarantee you, before they touch the rod, they start off as neutral, okay? That's somewhat described by this phenomenon right here. So something that you may have seen someone do at some point in your life is if you take a kind of like a party balloon and you blow it up and you rub it on your shirt, if it's dry enough outside, you can take that balloon and you can stick it to a wall. Has anyone here seen that before? California is pretty dry, so I would assume at some point in time some of you have seen this.
Yeah, I've seen it.
Yep. Okay. It's something that I always try to make work when I'm at school, but it never works. I don't know why. It's really hard to get it to work, but the idea is that everything contains charges. Your walls in your home are guaranteed, they're definitely neutral. They have equal amounts of negative and positive charges. But what happens is if you rub a balloon on your shirt, then it's going to gain some charges. Now, in this picture, they've decided to say that the charged balloon becomes positive. I don't think that's accurate, but it doesn't really matter. The point is, whatever charge the balloon has, when you bring it close to the wall, it causes what we call induced charge separation, as they say right here. And what that means is that within the molecules of the wall itself, the negative charges, okay, they're going to get drawn closer to the balloon, and the positive charges are going to get repelled away from the balloon, and it's going to make it so that locally the wall is kind of negatively charged. Even though the wall's neutral, locally the wall's negatively charged, and then the balloon can kind of stick to it. All right, and we call that it's basically it's induced charge separation. That's the word we use. So the same thing is happening in these little pieces of paper right here. Within the paper themselves, when the negative thing gets close, you've got this little piece of paper right here. Here's your little bit of paper. And here's your rod that you bring close that's negative. So the same kind of idea happens, that the negative charges within the paper basically they get pushed away, and the positive charges end up closer to the top. And as a result, this thing can be locally attracted to this. Because what we're going to find out pretty soon, when we talk about Coulombs Law, is the charges that are the closest are going to generate the biggest force, basically. So, and then just like the balloon sticks to the wall, the little pieces of paper will end up sticking to the rod. Okay? So that is effectively static electricity. Now there's a couple other things I want to mention about it, but let's before we talk about the other type of charging. So all of the things we're doing here with this rubbing can be described as charging by conduction or charging by contact. Let's just put it that way because that's really what it is. Okay, so it's charging by contact, which is basically like some kind of rubbing. And that rubbing process, well, it basically transfers these little charges around. But usually by the time you've taken this course, or you're taking this course, you already know kind of what's happening in these processes, right? there's a transfer of charges that's occurring, and that transfer of charge can really only occur via one type of particle. You want to know what particle that might be?
Electron.
The electron, yeah. How do we know it's not protons that are moving around? Okay, so basically what you're saying is this. You're saying the process of rubbing the fur on the plastic has the effect of taking little tiny electrons. So I've got my little electrons here that are kind of in my rod, right? And the rubbing process basically takes those... Oh, whoops, I did it backwards, didn't I? Sorry. Undo. Oops, okay. So the process that occurs here, basically what's happening is the fur has a lot of electrons, right? And by rubbing it, those electrons basically transfer down here, okay? Because the fur loses electrons, it becomes positive. Because the plastic gains electrons, it becomes negative, okay? Now, how could you say for sure, Baron, or anybody else that wants to answer, that you know that, and how can I say that I know that it's electrons that are being transferred and not something like protons, which we also know are charged, right? Protons have a positive charge, right?
Because if you change protons, the element itself changes.
Exactly, right. What's another reason? Yeah, the element itself 100% would change if you
The protons are inside the nucleus, so they can't escape.
yeah, they're inside the nucleus, which is they're strongly bound within the nucleus, right? That's exactly right. So the nuclear potential well is too big for them to jump out of, and even if they would, as I think it was Delvin said, it would actually change the molecule itself, which we know is something that doesn't actually happen very often, and it requires, well, in order to actually change the number of protons inside of a molecule, you have to basically split the atom, right? You need to bombard the atom with neutrons or something. You need radiation of some type to actually cause that to happen, or a lot of energy. Okay, so that tells us, that tells us everything we need to know about electric charges then. So electric charges themselves come in kind of three types, right? So you've got your neutral charge, you've got your positive charge, and you've got your negative charge. Okay. At a fundamental level, every one of these kind of has a particle that's associated with it. This one has a particle that's called the neutron, which is a neutral particle. This one has a particle that's called the proton, which is a positively charged particle. And this one has a negatively charged particle that we call the electron, right? Now, I guess a question would be, what do you know about the electron and proton charges? Well, let's back up a second. What do we know about electrons and protons? Which ones are bigger?
Proton.
The
proton.
Protons, right?
Proton.
So the mass of the proton in, I guess, SI units it's a very small number. It's 1.6 times 10 to the negative 27 kg. And the mass of the neutron is about the same, right? For all intents and purposes, these two are basically the same. The neutron is slightly bigger than the proton, but they're basically the same number, okay? The neutron is just a little bit bigger. There's other units we use for these things. One unit that we would use also is this one, 938 mega electron volts divided by the speed of light squared. This is a weird unit if you've never seen it before. I believe this is the right number. It's about 1 GeV. So a mega electron volt is related. It's an energy unit, okay, that we'll learn more about in the third chapter we'll do, chapter 23. Okay, but this is an energy unit, and you divide by the speed of light squared because Einstein told us that if you take energy and you divide by the speed of light squared, you get a mass, right? E equals mc squared. So this ends up being a lot more useful unit, as it turns out, both for physics 1c as well as for physics 1d, really much more for physics 1d. So you'll see both of these units when you look up mass of the proton. If you're working in SI units, you want to make sure you use this one. These are technically SI units down here as well, but you need to be a little bit careful. Maybe you need to, yeah, anyway. So that's that mass. Now, what is the mass of the electron compared to these? You guys said that the proton was bigger than the electron. Does anyone know roughly how much bigger it is? We can obviously...
Is it 2,000 times?
Yeah, it's about 2,000. That's almost exactly right. That's definitely the number that I go with. So it's 9.11 times 10 to the negative 31 kilograms. It's really hard to see just looking at those two numbers, but you can see negative 31, negative 27. That's a magnitude of 4 orders of magnitude. And this is a 1, this is a 9. It's kind of hard to see. But if you look at the mass of the electron in other units, the mass of the electron is 511. I hope I'm getting these numbers right. Feel free to look these up and check to see if I'm wrong. Yeah, so you can see that this is approximately, this is usually what I remember. This is 1 GeV, and this is about 0.5. No. Yeah. 0.511 MeV. And from there you can see that it's about 2,000, right? This is mega, this is giga. It's about 2,000 times as big. All right. So the electron is significantly smaller. That's part of why it's really easy for it to move around, because it doesn't weigh very much. All right. What do we know about the charges, though? How do the
Equal
charge...
and opposite
Equal and
of
opposite.
sign.
That's exactly right. So it turns out that the electric charge associated with the proton and the electron are exactly the same. There's no difference, there's not like a 1% difference, there's not like a 1 in 1,000% difference. They are exactly the same. So the charge of the proton is equal to the charge of the electron. The Q is what we use for electric charge, okay? The symbol Q is what we use for charges, okay? And the symbol that we give for this is the symbol E. And really what I mean here is the absolute value of this, okay? Because the electron is a negatively charged particle, the proton is a positively charged particle. And the symbol that we use for this is E, not to be distinguished from, or not to be confused with the E from mathematics, right? This is the E associated with the charge itself. So that E, we call that the electron charge, although it's the same thing as the proton charge. Oops. And it has a value. The unit we use for electrons, for charge in SI units is the Coulomb. And this is the number, 1.6 times 10 to the negative 19 coulombs. This is kind of the fundamental unit of charge. So for all particles that we've ever measured, apart from a few that I'll talk about in a second, all charges come in units of the fundamental electric charge, okay? So this is like one thing we would say is it's quantized, but I think that's something that can be kind of confusing. So the total charge on an object, on any object, so you use the symbol capital Q, would be always equal to some integer multiple, n, of the electron charge. And of course it can be positive or it could be negative. Of course you could make the n positive or negative if you want to, right? And so in this case, the number n is equal to 0, 1, 2, 3, etc. So charge always comes in some quantity of electrons. So for example, if I said that you have, let's say we have 15 microcoulombs of charge. Let's say I have an object, so I've got some balloon maybe, and let's say it has a charge, so I've got my balloon here, and let's say it has a charge of positive 15 microcoulombs, okay? You could ask the question, how many electrons does that have? Or how many fundamental electron charges is that? Okay, now it's a positive charge, so the number of electrons in this case is going to represent what? The number of extra electrons it has, or the number of electrons it doesn't have?
It doesn't have.
Yeah, so it's missing. How many electrons are we missing? Right? And that's really easy to do from our equation right here, right? We would just take 15 microcoulombs. We would divide by the charge on a single electron. Now you could put 1.609 if you want to here. There's more digits here, and we can figure out what that is. Maybe you can calculate this for me. What's this micro? We're going to see that come up a lot. What is 1 microcoulomb equal to? I'm sorry, I don't think I said this. I said it, but I didn't write down. 1C equals 1 coulomb, spelled like this, named after a French scientist. So what would 15 first of all, what's 1 microcoulomb? How many coulombs is that?
10
10
to
to
negative 6.
negative 6.
Yep. Okay, so then how many electrons are missing from this then? If we do 15 microcoulombs divided by 1.6 times 10 to the negative 19. I could have chosen 16 microcoulombs. That would have been a much better choice. Can you calculate that for me?
got 9.37 times 10 to the 13.
That sounds about right. Definitely should be something like 10 to the negative 13. Yeah, I got the same thing. So it's about 9.4 times 10 to the 13. We'll just round up to 2 sig figs. So 9.4 times 10 to the 13, and we'll just say electrons. So that's how many electrons have been rubbed off of this balloon, basically. Right? Okay, so there's some ways to quantify electric charges. We use the symbol that's called the Coulomb, and 1 Coulomb is a lot of charge. One thing I would say, I guess if you want to understand what a Coulomb is, we can relate it to something that we don't really see very much here in California, but certainly you have some experience of it. So in a thunderstorm, when lightning strikes, and this is by no means a hard and fast number, this is just roughly. When you have a lightning strike, what's really happening is that the cloud has either become negatively or positively charged, usually positively charged, and it becomes so heavily charged that eventually that charge just really can't be contained within that region, and a lightning strike occurs. This is something that you experience when you shock yourself, like when you open a car door, or when you scuff your feet on the floor and you go and touch one of your siblings or something like that. You can shock them, right? It's the same idea. If you get too much charge in one place, then eventually it will cause this discharge to occur. When that happens, there's a transfer of about 15 coulombs. So one lightning strike is about 15 coulombs of charge. Now, if it's a small lightning strike, it might be like 1 coulomb. If it's a big lightning strike, it might be 100, but we'll just call it 15, somewhere in that region right there, right? So that tells you that's a lot of charge, right? If that much charge was to kind of go through your body, it would certainly cause damage to you. And yeah, so 1 coulomb is a lot of charge. Just something to keep in mind. And that's why an electron has such a small amount of that charge. Okay, so are there any questions? One other thing to mention about this is that charge is a conserved quantity. So electric charge is conserved in all known processes. So that actually means that this is your 4th or 5th conservation law you learned about, I guess, depending on what you've taken so far. So in Physics 1A, you learn about conservation laws, and they're really important to physics, right? The conservation of energy, momentum, angular momentum, right? Oh, I left a word out here. It's electric charge. Sorry. Electric charge is conserved in all known processes. So here's another conservation law. Electric charge is always conserved. You can't have electrons kind of appearing out of nowhere. And if you have a flow of electrons from one point to another, anything that flows in one side has to flow out the other. Okay? So, yeah, electric charge is conserved in all known processes. Now, let's talk about a special type of charging. We talked about charging by contact. Let's talk about charging by induction. This word induction is going to come up a lot in this class, but it's going to kind of mean slightly different things. Oops. I just want to cut this. Control cut. Why is that not working? Oh no, what did I do? What did I do? We'll just drag. I don't know what's going on with this thing. Just drag this down here. Okay, so here's a little picture of charging by induction. We'll go through it step by step. Probably should have talked about conductors and inductors and insulators, but we'll talk about that next. Okay, so we got a metal ball. And we have an insulating stand. The insulating stand means that charges are not going to be allowed to flow very quickly through this. We'll just assume they can't flow at all. Okay. The ball starts off as neutral, right here. We're going to bring a negatively charged rod close, but we're not going to touch, so these two are not touching each other. Similar to what happened with the balloon that we described earlier, these negative charges will basically push electrons to the right-hand side of the ball, which will leave the left-hand side of the ball positively charged. Okay. The next thing that we do is you take a conducting wire, and you place the conducting wire in contact, right, with the metal ball. As a result, and you connect this wire to the ground, okay? What does that mean? Well, it could literally mean that you stick a rod in the ground that's metal, and you connect the wire to it. In fact, I know for a fact, like at El Camino, that we use things like this. I mean, all electrical systems have to be grounded, which means they need to have a wire that flows to the ground. And in almost all situations, it is quite literally a pole that is stuck in the ground that the wire is attached to, okay? And all that does is it gives a path where the electrons can flow into the ground. And ground literally means earth, right? So because these negatively charged particles are repelled from the negatively charged particles in the rod, they basically need to go as far away as they can. And by introducing this wire, they're no longer contained within the system. They're just going to flow out, okay? The next thing we do is you cut the wire, okay? You remove the wire, and what's left over is a positively charged ball, basically, okay? Once you remove the negatively charged rod right here, the positive charges are basically going to go ahead and distribute themselves out again, okay? Really what's happening is negative charges are coming back to fill in the gaps, but there's less of them now, right? Because you remove them with the ground. So we call this charging by induction. It does not require contact, right? All we did was we brought a rod really close, and we used a wire to basically siphon off the electrons. And then once we've done that, what we're left with is a positively charged object. And the ground is now slightly more negatively charged, although the Earth being slightly more negatively charged is not going to make really any difference, right? So that's what we call charging by induction, okay? And if we were at the school, I would actually have you do this. It's harder than it looks. There's a lot of things that are difficult about it. One is that when you bring the rod close to this, there's a tendency for static discharge to occur. Meaning that this rod, when you bring it really close to this thing, if you bring it too close, you might get a little static shock right here. Does anyone want to guess what would happen? What charge would end up on the ball if that happened? So if I take a metal ball, right? Neutral ball, right? And I bring a negatively charged object near it, like this. And I get close enough to where I see a spark that occurs between here. Okay, and maybe you turn off the light so you can actually see it. What do you think is going to happen when that spark jumps to here?
The ball will be negative.
Yeah, that's exactly right. So what ends up happening is the ball ends up being negative. The rod actually may end up being neutral if it transfers everything, but it could have some residual negative charges. But either way, that little static discharge is quite literally it's a flow of electrons into this object. Does that make sense? Anytime you've ever been shocked, that's literally because there's a flow of electrons either going into or out of your body, right? Which way doesn't really matter, because you're still going to feel the shock, right? It doesn't matter if the electrons are leaving your body or entering your body, you're still going to feel that shock. So yeah. So that's part of what makes this difficult. If you get too close, you'll get static discharge and it'll ruin it. So you have to stay just far enough away to have the effect work. And it turns out to be, it's kind of actually challenging to make this process work, but it works. Okay, we call that charging by induction. Okay, so let's get some more. I used some words here that I probably should have defined first. Okay, so let's talk about what a conductor is and what an insulator is. I think it's somewhat acceptable to use these words without fully defining them because I think you all know kind of roughly what they mean. The question is, do you know what they mean in kind of like the way we want to understand it for physics? So a conductor, how would you define what a conductor is? An electrical conductor. What does that mean?
Something that like readily takes on electric charges.
Okay, and what was the other explanation that was being given?
It can transfer electrons freely.
That is a better explanation, yes. You're both saying roughly the same thing, though. So a conductor allows electrons to flow easily between its parts. And then you all know examples of what conductors are, right? It's basically just metals, right? Almost all metals are good electrical conductors. Often the way we think about these metals is as if there is a kind of sea of electrons that are free to kind of flow all over the place, almost like a gas. these electrons kind of behave like a gas once they're inside the metal. In general, what ends up happening is that in a lot of metals, the outer electrons are not nearly as tightly bound, and the electrons are basically free to move all over the place. And this property of conductors is core to all electricity production, right? When I want to transfer electricity from one location to another, all you need is a metal wire, and that metal wire will allow you to do that, okay? So an insulator is exactly the opposite. Electrons tend to be bound. And we'll just say it's kind of the opposite. They're not free to move. Now, it doesn't mean you can't remove electrons from an insulator. It doesn't mean you can't add electrons to an insulator. We looked at an example of that earlier with the plastic. So a piece of plastic, so an insulator could be something like plastic. It could be wood. It could be air. Things like this. Things that are kind of non-metals. Yeah, it just takes a lot more work to actually make the electrons move. And even when you move them, the electrons aren't really free to move around with the object. Okay, so that's a conductor and an insulator. And then there is one other type of object that kind of falls in between the two of them, which is called a semiconductor. Semiconductor are things like silicon, and you all probably know that they're very, very important for electronics. And the difference for a semiconductor is that, I'm not going to write this down because this is kind of a little bit beyond the scope of this course, but it's important to understand a little bit. Semiconductors can have their conductive properties altered by the addition of other types of things. So if you take silicon and you do a process that's called doping, where you add other types of material to it, you can kind of alter its conductive properties. And they work a little bit different. Their entire course is just on semiconductor physics. I'm not going to go into a lot of detail about it today. But later on, we will talk about this again when we get into understanding what electric current is, and when we understand more about how temperature affects resistance. We'll talk more about conductors, semiconductors, and then yet another type of material, which is called a superconductor, which is like a perfect conductor. Okay, so for now, all we really need to know about are conductors and insulators for what we're going to be doing. All right. So what is next? I think we're ready to start talking about electric forces. I think our next thing is Coulombs Law. Yep. Just trying to think. I don't think we missed anything. Now, I didn't cover absolutely everything your book does. Your book goes into a lot of detail about more of this stuff. So feel free to read the book if you want to. There's a lot of good stuff in there. Okay, so let's get into more of the normal kind of physics stuff. So now we've described what charges are, and what we would like to know now is how strong are these electrical forces? We know that positive charges repel each other, negative charges repel each other, and different charges attract each other, but how hard do they attract each other, right? So Coulombs Law tells us that answer. How big is the force of electricity? All right. So Coulombs Law refers to, I'm just going to give it to you exactly as it is. So suppose that I have two charges. So I have one charge right here that I call Q, and I'm going to use a little circle around it to represent, this is kind of like a ball of charge. It could be an electron, it could be a proton, it could be whatever. And we'll say that this has a charge that we call Q1. All right. And over here, nearby, we have another charge that we call Q2. And for simplicity's sake, let's assume that these charges are kind of in outer space. They're nowhere near anything. The only thing that they can see is each other, basically. Everything else is too far away. They can see distant stars and stuff, but there's two things floating in space. And we'd like to know exactly how big is the force that exists between the two of these. Okay, so what we do is we need to know the distance between the objects. So if we connect the centers of the objects, we need to know that distance between the two of them. Let's draw a line like that. So we'll call that distance R. R. And that's all we really need to know. We need to know the size of the charges and the distance between the two of them, because Coulomb's law basically says that the force between these two objects, which we call the electric force, is going to be proportional to, so there's the proportionality symbol, the size of the charges multiplied by each other, Q1 times Q2, and then you have to divide by the distance between them squared. Now, if these two charges are the same, what direction is the force going to be? Like on the left charge. What direction, if Q1 equals Q2, if they're both positive, let's say, what direction would the force on Q1 be?
Outer to the left.
To the left, yeah. Okay, so let's use that as our reference point. So let's say that the force on Q1 is this way, and I'm going to call that the force of 2 on 1. And then on the other side, if they're both positive, so if this is positive and this is positive, the direction of the force on this side is going to be this way, right?
Mm-hmm.
Now, which one is going to feel a bigger force? Let's pick some numbers here. First of all, let's say that the force on the left, the charge on the left, let's say Q1 is equal to, let's use a simple number, 2 coulombs. And let's say the force on the right, Q2, is equal to 4 coulombs. Okay? Which one's going to feel a bigger force? Is it going to be Q1 or is it going to be Q2? And you can write your answer in chat. Which one's going to feel a bigger force? Q1, Q2, or neither? Okay, pretty quickly, a lot of people answer Q1. That's the natural thing to say. DeHouse says the same. Okay, now the reason why you think it's going to be Q1 is because Q2 is bigger, right? It's that simple, right? Q2 is bigger, so you think, oh, the force on Q1 has to be more because you got 4 coulombs over here. But there's a rule from Physics 1A that tells us why that's wrong. What's the rule from 1A that tells us? So someone got it right. It was DeHouse. DeHouse's the one that got it right. The answer is that they feel the same force. What's the law from Physics 1A that tells us why that's true? You
The
remember?
forces on both of them are equal but opposite direction.
Yeah, exactly. What's that called?
Is it Newton's third law?
That's right, the third law. The third law tells us that these two forces have to be exactly equal and opposite to each other. So the force of 1 on 2 has to be equal to the negative of the force of 2 on 1. We call that Newton's third law, right? But it's really common. I mean, certainly when I would think about this, if you just don't stop to think about it, it seems like Q1 should feel a bigger force, but they don't. They feel the same force. And what that force is, we call that the electric force. Okay? The magnitude of those two values is the electric force. This doesn't exactly... There's some issues here, but yeah, actually, I guess a better way to write this would be just to say the magnitude of each of those forces, F12 is equal to F21 is equal to the electric force. And here, without the vectors, I just mean the magnitude of the forces. I can be more clear by doing something like this. Okay. Okay. So we know that they've got a force like this. Now, really, what you want to do is you want to kind of say, if one of these is negative and one's positive, you force it to be attractive. But you could, if you really wanted to, say something like this. The force that they feel is equal to... So we can put an equal sign in here, and to do that we need a constant. We call it the electric constant K. Q1, Q2 divided by the distance between them squared. Okay. What you could say is that if one is negative and one is positive, you put the negative sign in here, the positive sign in here, you're going to answer that's negative, right? And if one's negative and one's positive, what are they going to do? Are they going to attract or repel?
Attract.
They're going to attract, right? So you could just basically, you could create a, what do you want to call it? A convention by which you said that if you get a negative answer, it's attractive. And if you get a positive answer, it's repulsive if you want to. But really the better way to do it is just to say, this is the magnitude of the force, okay? And you figure out the direction based on, what's positive and what's negative, right? Okay. But that is Coulombs Law right there. Now, of course, I need to define what the K is. So the K is a constant that Coulomb himself figured out, and it's equal to about 9.9 times 10 to the 9. No, not 9.9. What am I talking about? So sorry. Excuse me. It's something like 8.988 or something like that. So usually what we do is to keep this really simple in this class. This will work for certainly all of your homework problems. We just say it's 9 times 10 to the 9. That's really easy to remember, right? 9 times 10 to the 9. Okay? And the unit for this basically is just a unit that makes it so that the thing on the left side ends up being force. So you can figure it out pretty easily. First of all, we want to get force, so we know we're going to have a Newton right here, right? And in order to get a force, well, we're dividing by distance squared in the bottom. So I better multiply by that, because that'll cancel out with that, right? And then I also have Coulombs squared in the numerator up here, so I better divide by Coulombs squared. And we call that the electric constant. I think it has other names. Usually we don't write the E. Usually we just write it as K. So that's the electric constant. Now there's other versions of this that you're going to see, so I'll go ahead and write the other one. And I think this is probably the version that Coulomb himself would have written down. So the other version of this is where we replace k with this symbol, 1 over 4 pi multiplied by epsilon naught, and then you've got your product of the charges, q1 times q2, and then you divide by r squared. So that's the other version. And if you compare these two equations, you'll notice that they both have this k and then this symbol here. So you can identify that the electric constant k is equal to 1 over 4 pi multiplied by epsilon naught. You might be like, what's the point of that? Why would you ever use this thing? Well, you really get away with never using it. But the truth of the matter is that a lot of our equations get a lot simpler when we use this symbol epsilon naught, okay? Now, you can figure out for yourself what epsilon naught's equal to. It's basically equal to 4 pi multiplied by k to the negative 1, right? And if you plug in the constant k right here, you should be able to show yourself that this is about equal to about 8.85 times 10 to the negative 12. And then because it's the inverse of k, it's going to have the inverse units. So it's going to be coulombs squared divided by newtons times meters squared. Okay, they're both equivalent. They both work. You can use whatever you want. I know in the lab manual you're going to see epsilon naught show up a lot, and I know in your book you will as well. You need to know what both of them are. This one has a nice name as well. This is just called the electric constant K. Epsilon naught is called... Oh. I think it's this. Permittivity of free space. I think that's a pretty cool name. The permittivity of free space. I think that's the right one. It's either permeability or permittivity. I think permeability is for magnetism. I think permittivity is for this. Now, the fact that it says free space right here might make you think, oh, well, is it different for like Earth and like air and like, is it different for other things? And yeah, the answer is yeah. There's a different version of epsilon depending on the medium that you're in. So free space, like outer space, this is the value. But on Earth, if you're in the air, for example, the value is slightly different, although with air it's kind of not that much. But if you're in glass, if you're in paper, there's all kinds of different values of this thing here, right? But in general, here's our force law. The force law isn't going to change based on, well, yeah, we'll leave it at that. Let's do a quick calculation. So we use the numbers of 2 coulombs and 4 coulombs up here. Let's say that these two objects happen to be separated by, let's say, 0.5 meters. Okay. And let's see if we can come up with a calculation for exactly how big the force between these two objects would be here. So the electric force between those two objects should be equal to, so we've got all our numbers and we've got our equation right here. I'll try to keep everything on the screen at the same time. So we would basically take our number k, which is 9 times 10 to the 9, and we'd multiply by our charges. So one of them is 2 coulombs, one of them is 4 coulombs, and then we just divide by the distance between them squared. So 0.5 meters whole squared. And that would give us some kind of a number. We'd probably do this on our head, because this is going to be 4 times 4 is 16, times 2 is 32, 32 times 9, that's like... something like this. Can you calculate that and tell me what you'll get? You look at the units, the meter squared cancels with the meter squared, the coulomb squared cancels with coulomb times coulomb. That's what you get. 280, okay, so this number's huge, right? This goes back to something that I said earlier. A coulomb is a lot of charge. If you had these two objects that were separated by a coulomb, they would feel a force. I mean, it's probably a few tons, right? What would that be in pounds? So in pounds, you would divide by what? About, you divide by 4, right? A newton's a quarter of a pound, right? So if you divide it by 4, you're going to get 72 times 10 to the... This isn't exact. This is close, though. So it's something like 72 times 10 to the 9 pounds. 72 billion.
That's gnarly.
Yeah, it's a huge number, right? 72 billion pounds. This is a huge number. So again, this is because 1 coulomb is a huge amount of charge. But there's another thing that's playing into this, right? This number is gigantic. You no matter what your charges are, and no matter what your distances are, you end up multiplying by 9 billion at the end. So as a result, normally what we'll be using are probably microcoulombs of charge, and the distances may be smaller. You'll notice that what happens to the size of the force is the two objects get closer together. So for example, let's say that I give you two reference charges. I've got one charge Q1 and one charge Q2. And I place them at some distance, and I call that distance r apart, okay? If I was to take those two charges and I was to place them 2r apart from each other, what would happen to the force? So if I double the distance between the two of them, so it's 2r, and I tell you that the force in the first case was repulsive, and it was like this, what's the size of the force now? F over 4. Exactly, it drops by a quarter. So this would be F over 4 on this guy, and this would be F over 4 on this guy. So the larger the distance becomes, the smaller the size of the force, which tells you that electric forces are going to be strongest when things are closest to each other, right? The closer two objects get, the bigger the force is. Now, there's a lot of things that we can say. What's up? Okay, I think someone's just queuing by accident. All right, so the closer together they are, the bigger the force is. The farther apart, the weaker the force gets. The bigger the charges are, the bigger the force is. That's what we know about this. Now, there's some interesting kind of like questions that we can create into this. We talked earlier, and one of the things that someone said about the plastic rod, I asked the question, how do we know it's electrons that are transferring and not protons? And someone said, well, because if a proton transferred, it would change the molecule, which is right. And the other thing is because the nucleus itself is containing the protons, right? To get an idea of what that means, let's think about what a nucleus is. So let's look at like the nucleus of a helium atom, for example. So a helium atom has how many protons? Helium.
2.
Two.
We're going to talk about helium-4. So 2 protons, and then what else does it have?
2 neutrons.
2 neutrons. So we got an N0 for neutron. Okay. So that is our helium-4 nucleus, right? We're just looking at the nucleus. We don't care about the yeah. Now, do you guys know anything about how big a nucleus is? Like, how close together are these protons exactly?
They're packed in there.
They're tiny.
It's really small, right? The diameter of an atom, I think, is about 10 to the negative 10. I think the size of a nucleus is about a femtometer. So I'm pretty sure the distance between these guys is on the order, we'll call it r, is on the order of 1 times 10 to the negative 15 meters. And if you were to take that number and then take the charge of the protons, we can actually calculate the force, right? Let's just do it real quick here. We're going to take a break, I promise. But so the force, electric force between these two objects, let's use this number here. We would take K, right? 9 times 10 to the 9. And we would multiply that by the charge of the proton. So the charge of the proton is the same as the charge of the electron, 1.6 times 10 to the negative 19. And we have to square it. And then we divide by the distance between them squared. Now, even though we have to multiply by 10 to the negative 19 and square it, we're dividing by 10 to the negative 15, and we're squaring that too, and then we still multiply by 10 to the 9. So we're going to get a pretty big number here. In fact, I don't really care about the other things. Let's just look at the exponents, right? So 10 to the negative 19, 19 minus 15. Wait a minute. Plus 15, right? Yeah, add it. Would be 10 to the negative 4. And we'd square that, would be 10 to the negative 8. We multiply by this. You're going to get something on the order of something like 10 newtons, I think, right? Does that sound about right to y'all? Going through this kind of fast. Now, that might not seem like a big force, right? But the proton's tiny, right? So the acceleration that proton would feel due to that force would be the force divided by the mass of the proton, which means you're taking the force, which is about 10 newtons. I'm probably way off here, but it's order of magnitude probably about right. Maybe you guys can check that for me. Oh, I think I did it right. The proton has a mass that's on the order of 10 to the negative 27 kilograms, right? Which is going to lead to an acceleration of something like 10 to the positive 27 meters per second squared. That's a huge acceleration that the proton would feel, right? The force might not seem very big, but 10 Newton force on something that only weighs 10 to the negative 27 kilograms, right? Or has a mass of that. That is a massive acceleration that this object would experience. It would accelerate to the speed of light within milliseconds, not within like nanoseconds, right? So that's the kind of force that this proton is feeling. It's a force that would cause an acceleration like this. However, Protons don't escape from the nucleus on their own, right? They're stably bound within these things. And why is that? If there's this giant force,
Strong force.
yeah, there's another force inside the atom that actually holds these guys together, and we call that the strong force. So why do you think we call it the strong force? We call it the strong force because it's stronger than electricity and magnetism, which before we discovered the strong force, electricity was the biggest force that we knew. And it's one of the biggest forces we know because of this gigantic multiplier that we have to put on the front of it. Electric forces, by comparison with gravitational forces, are completely different in terms of size. You multiply by 9 billion here, but in terms of gravitational forces, you actually multiply by something like 10 to the negative 11, right? So they're orders of magnitude different from each other. The electric force is gigantic, but there's a bigger force out there. There's always a bigger fish. In this case, the bigger fish is the strong force, and that strong force is enough to hold together the nucleus of the atom. And it turns out it doesn't just attract protons to protons; it also attracts protons to neutrons, and neutrons to neutrons. It basically attracts nucleons to each other. Now, this force only matters when you're really, really, really close together. This force only starts to matter when the objects get super close together. Before that, it just doesn't have much of an effect. And that force holds together the nucleus, and that's why you can't actually just rub fur on a piece of plastic and expect protons to suddenly start popping out.